Hello everyone. We are the students of Anna Saheb Dange College of Engineering and Technology, Ashta, from the Department of Aeronautical Engineering. We are here for the presentation for the subject of Advanced Propulsion System, and we are presenting one topic which is types of nuclear propulsion systems. And this PPT is presenting by the Kazim Sheikh, myself, and my colleague Vishal Shinde. Now we will see the different types of nuclear propulsion system one by one. Now, nuclear propulsion system. What is meant by nuclear propulsion system? In this process, high energy is produced. Which can be used for a power or propulsion purpose, or we can say that we can use it for the generation of high power or propulsion or for a propulsion purposes. In this 1 gram of uranium can produce 2.5 million times energy produced by 1 gram of coal. With the help of that, we can come to know that how much amount of energy is produced from the uranium. And there are two types, nuclear fission and nuclear fusion. And in this figure we can see that nuclear fission process. So there is a diagram. In this we can come to know that the nuclear fission process and application of that is nuclear reactors. And here is a one reaction is there for a nuclear which is come under a nuclear fission. Nuclear fission is achieved by bombarding a neutron to highly unstable nucleus. This results to nucleus to split into two pieces. And in this there are two cores, like solid core and liquid core. In that we can come to know with the help of the diagram. In the solid core, working fluid, middle part is a solid reactor, and then nozzle is there, and last one is hot gases produced. In the solid core, nuclear reactor as a heat source, and fuel element contains uranium carbide particles. And in liquid core, the working fluid can be heated above the nuclear fuel melting point. And that disadvantage of a liquid core is the loss of fissionable material with the propellant. It means there is a loss of a fissionable material with the propellant. In that, the parts of the liquid core are working fluid, and then it passes towards the liquid nuclear fuel, and there is a moderator, and after that nozzle is there, and same as that of solid core, there is a hot gases produced. And the another one is a gas core. In this, a high specific impulse is estimated, and nuclear fuel is contained in a high temperature. Plasma and radiant energy is transmitted to the propellant. And in the gas core, the propellant used is a liquid hydrogen. And another one is a fission fragment propulsion. In this, uses the energetic fragments produced in the nuclear fission process directly as a propellant. And propellant velocity and specific impulse is high as compared to the other cores and other propellants. And in the diagram of fission fragment propulsion, we can see that there are parts are there: graphite fiber with the nuclear fuel on surface, magnets are there, reactor core, and last one is nuclear exhaust plasma. The nuclear fusion propulsion system. If two light nuclear cores are used together, or we can say the two light nuclears we can combine together, like example hydrogen. The resulting heavier nuclear element has a binding energy than the sum of two original ones. There is a one reaction in a nuclear fusion propellant system. This is the only fusion reaction which has higher cross section available and requires relatively low initial energy, equivalent to 10 kil kilowatt is equal to 25 Kelvin, that is equal to 25 million Kelvin. Applications of nuclear fusion propulsion systems are energy needed to overcome electrostatic propulsion between two positively charged nuclear cores, and another one is cross section available for nuclear core is very low, which requires higher density nuclear core. And the third one is keep confined on plasma so that it does not touch the chamber, maintaining high density. Now the types of nuclear propulsion fusion propulsion system and its types will be explained by my friend Vishal. Over to you, Vishal. Vishal?
Thanks, Kazim. Now I will explain about the nuclear fusion propulsion system. Uncontrolled fusion has been achieved by a thermonuclear fusion bombs. Controlled fusion along the development of a fusion power plant is still under heavy development. A famous saying since 40 years is that controlled fusion is 10 years away. There are mainly three types of nuclear fusion propulsion system. First one is inertial confinement fusion, second one is magnetic confinement fusion, and third one is inertial electrostatic confinement fusion. Next slide. Now, inertial confinement fusion. A pellet containing a fusion is placed in the focus of either laser or particle beams where it is heated and compressed. It is shown in figure. Fusion reaction inside the pellet create a high temperature nozzle to create a thrust. The pellet's own inertia is sufficient to confine the plasma long enough to so that is useful. Fusion reaction can be sustained in a variant called magnetically insulated inertial confinement fusion. An additional metallic shell is added to the pellet. During laser particles bombardment, electrons leave the surface of the outer surface, which creates a magnetic field. This enhances the confinement and leads to a higher fusion power gain. Now, next slide. Now, magnetic confinement fusion. Magnetic confinement fusion device only confines fusion plasma by strong electromagnetic Lorentz forces. The plasma can be kept inside a magnetic bottle heated by a high frequency electromagnetic field coils. High energy plasma can then escape through leak in the magnetic field configuration. Another possibility is to compress, confine, and direct the fusion plasma in one magnetic pinch created by a powerful discharge between a cylindrical anode and a rod-shaped cathode. The magnetic field lines concentrate around the cathode, increasing the Lorentz force and forming a plasma focus. If the magnetic field is sufficiently dense, fusion reactions will occur and the plasma is expelled through the magnetic gradient. from the fuel inlet to the outside. This device is therefore called dense plasma focus thrusters. Kajum, next slide, please. Now, inertial electrostatics confinement fusion. It is shown in a figure. Electrostatic fields can also confine a fusion plasma. This can be accomplished by applying a high electric field between a mesh-shaped electrode and an outer shell. Positive fusion fuel ions are injected to the grounded outer shell and accelerated towards the mesh electrode. It means typically at up to minus 100 kilovolt with respect to the outer shell. Inside the mesh, the ions gain enough energy to perform fusion reactions. The plasma can escape from a hole in the mesh electrode to create a thrust, and it developed at the University of Illinois in the United States. Small scale I fusion devices are already commercially available as portable neutron sources. Upscaling of these devices is investigated. Kajim, next slide, please.